Good evening and welcome to another online session of question answers. This is the course on Introduction to Wireless and Cellular Communications. This is Professor David from IIT Madras, and welcome to the students who are joining us online. This week we have been studying week 7. We have been This week we have been studying the aspects of diversity. So maybe we can give a theme for the entire week as the topic on diversity. And to preceding that, we looked at the ways in which we can generate on a computer the fading, the characteristics of a fading channel. So computer generation of fading, computer generation of relay fading, that has been the first part of the week. And then we looked at Jake's model. That is one of the most widely used models that we have for generating any type of fading environment on for computer simulation purposes. And then we saw how much the signal can fluctuate. And then based on that, we gave an introduction to antenna diversity. So that was the last 3 sessions pertain to the aspects of antenna diversity. So understanding the wireless channel, generating it on a computer, and then trying to look at the benefits and the need for antenna diversity and for the different ways in which we can study that. So this has been broadly the coverage of topics in the course, and we hope you've had a chance to look at the lectures, also look at the assignments, and if there are any questions, please feel free to post them online. So let me just say a few words about the importance of diversity. When you look at a channel that is experiencing relay fading, you can think of it in the following fashion. There is a transmitter and we have a receiver. This is the receiver. Now, the channel between the transmitter and receiver is experiencing a fade. So therefore, I kind of write a block saying that that particular copy of the signal will not be received. So this will lead to a situation where the receiver will not be able to detect the signal correctly, which we would call as outage. So for this red antenna at this moment, this would be a situation of outage. So if you were to look at it as a function of time, and this is signal strength, you can see that the fluctuations in the signal strength could be some variations. Some some places it's a little bit better, sometimes it's not so good. So if you think of the threshold for a fade as something like this is the threshold. Anything going below the threshold will cause the signal to go into outage. So for example, the antenna, but the channel between the transmitter and receiver, you could think of it as potentially in a situation that is in a fade. So these shaded portions would correspond to a fade. Now, what do we do in the context of a fade? We do not know where these fades will occur or when these fades will occur. So therefore, we cannot increase by compensating for the power. The other thing is you have limitations on how much we can increase in power, because occasionally the fade can be of a very substantial depth. So you can see that the fade compensating it by increasing the power could sometimes be a challenge. So the best option that we have in such a situation is if there is a second antenna which can pick up the signal and process it. So hopefully the second antenna signal at this point is something that is uncorrelated, and therefore you can switch between the one antenna and the second, and therefore get the benefit. Now, what happens? What is the best way? Supposing you have two antennas, what is the best way of combining? So you can do the methods of combining. Methods of combining. The first one is, of course, just simple selection. Methods of diversity combining. One is simple. It is selection. Select the stronger of the two antennas. Second one is what we would consider as the optimal method. It is called the maximal ratio combining. This will be studying in the next week. And there are suboptimal methods. I'll just write them as suboptimal, something that is somewhere between selection and maximal ratio combining. Okay, so this is broadly the framework of diversity, and what we have studied today is the use of Jake's model. So you can, using Jake's model, you can generate a waveform that looks like the red graph that tells you how the signal will fluctuate up and down. You can also use the Jake's model for the generating the orange. Those would be uncorrelated waveforms, uncorrelated fading waveforms using these. So multiple instances of the Jake's model can be used to generate these uncorrelated or independent fadings channels. Okay, so broadly, this is the framework of what we have been covering in the class. Diversity is a very important technique. So in the 2G systems, the base station employed diversity, and it had two branch receive diversity. So when the mobile would transmit, the base station would receive with two antennas, and therefore you could then combine. Then from to 3G and 4G and eventually to 5G. So in this progression of cellular systems, we went from two antennas to 4 to 8. Then we said that there would be multiple antennas both at the transmitter and receiver. So you could have a 2x2 system, 4x2 system, 4x4 system, then 8x8, and dot dot dot. So this is where we get into all of the different MIMO modes. These are referred to as the MIMO. In our course, we will be touching upon MIMO, but that is at a later date, in a later week. But for now, what we'll be focusing on is the aspects of diversity and how do we combine them. So that is broadly what we have been looking at in the course of this week. More interesting topics to come up in the following weeks. Any questions from the student side? I'll be happy to take it up. Now is the time to switch over from questions down onto the. Okay. How to design the data link for these types of networks between satellite to Earth stations. Excellent. So let me see if I can pull up my presentation. I may have a slide on that. I will see if I have the deep space network. I'm just seeing if I have the slide on the deep space network. Just give me a minute. I had intended to address this very specifically. Okay, it looks like I don't have the slide on the deep space network. Let me explain using the pad, and then in the next class I will bring you a I'll bring a slide with all the details. So the deep space network, NASA's deep space network. Here is what it is in a nutshell. So basically, we have a ground station with a very large parabolic antenna communicating with a spacecraft that has gone outside, in fact, in some cases, gone outside of our solar system. So basically, what is happening is there is a communication which is happening with respect to the with the satellite's signal being received with very low power. So let me see if I can highlight it in this fashion. So typically, a link budget has the following elements. This is the transmitted signal power. If there are any losses in the transmitter, that would be the negative. That would be the losses. I'll just write it as L for the loss. On the other hand, if we get a gain, if the transmitter antenna has a gain, you will see that this is the gain of the transmit antenna. This is the gain portion of it. Once you have reached this point, this is what determines the EIRP, the effective isotropic radiated power. So that's the power level with which the transmitter is transmitting. And then you have the drop due to the path loss. And at the receiver, what we do is we can then amplify the signal to get the a signal level up. So this is once again a gain term. This is the gain of the receive antenna. And then you have the implementation of the receiver. So this is the receiver noise level. This is the signal level. This is signal level, and the difference between these two will be the signal to noise ratio. Now, what we see with the deep space network, so this antenna has got a very large gain antenna. So in fact, there are 3 of them located at 3 different locations which are picking up the signal. So one more antenna I can draw, 3 locations across the globe, and all of them are picking up the signal. And the information is then shared between the 3 of them, and then the signal strength is received. So effectively, you can think of it as a transmission scheme or as a receive scheme which has got a very large gain. So even though, let us say, we are looking at the downlink, the spacecraft is transmitting with very low power, and because of the distance, there is a very significant path loss. How do we still pick up the signal? Because on receive, the antenna gain is very substantial. The antenna gain on receive, so that will boost the signal, received signal, very, very substantially. How does it do that? Because it has got 3 large gain antennas picking up the signal, and then you combine them to get a even better signal. What is the advantage on what do you do for transmit? The transmit also, because of the distance and the path loss that must be overcome, the transmit the signal is transmitted with sufficient power and with the high gain antennas. So therefore, you can still reach the spacecraft even though it's at a very large distance. So very quickly, the key elements that we would see are a high gain antenna system and the notion of diversity, because 3 antennas are picking up the signal and then combining the information. So the key elements that I would say of a deep space network, DSN stands for Deep Space Network. One is the large gain antenna, or antennas in this case. Okay. And the second one is the diversity antennas. You have multiple antennas, large gain antennas. And the third one is the transmit with high power in order to reach the spacecraft and achieve receive gain, high RX gain. to receive the signal from spacecraft. So this is to receive signal from spacecraft. Okay, and high transmit power is to reach the spacecraft. And the other very fascinating thing is the use of channel coding. Because you have very low signal to noise ratio, you want to get the most powerful codes. So the key element of the DSpace network is channel coding. So they use a technique called concatenated codes, and constantly they are working on concatenated codes, and these are very powerful, close to capacity achieving codes, concatenated coding schemes. And so combination of very good design of the communication front end, and also the channel coding for the processing. Okay, I will get a few more details in terms of the dimensions, the gain that's achieved. But for now, this is the information that I have. I will make sure that we augment this information in the next class. Question number 2: how does the aircraft communicate with air traffic controllers of the airport? Okay, air traffic control communication between air traffic control and the aircraft. There are dedicated channels that are available for the transmission, and specified frequencies, and they have the ability to connect to the different air traffic control. Now, one question maybe is how are we handling the case with the Doppler being so high? If you notice that the aircraft is at a certain height. Let me see if I can sketch for you an aircraft. Okay, and you are communicating with air traffic control. So okay, some a building far away, which has an antenna that is picking up the signal. So okay, and what we will find is that mostly the air traffic control communications, a lot of it happens when you are in reasonable range. The key thing to note is that in a terrestrial system, when supposing this was a base station, and we had a car that was a car, and this was moving, you will notice that the Doppler, the direction of transmission and the direction of motion can be either away or towards. So therefore, you get a very significant Doppler component. Okay. Notice that in the case of the aircraft, the direction of motion of the aircraft is in a particular direction, and the direction towards the air traffic control is different. So therefore, only a component of the velocity contributes to the Doppler, and therefore the Doppler can be the Doppler is less. However, the aircraft's speed is much higher, so therefore, we have to take that into account. We have to design systems that are highly robust to Doppler. So that is something that we can easily do in a communication system, and therefore not an issue. So the two things that I wanted to highlight as an answer to this particular question. One is the effect of Doppler. How does it affect? It's different from what you would see in a terrestrial communication system. The second one is that it has to be a very robust receiver in order to handle whatever Doppler is present in the signal. Okay, third question. High-speed aircraft, especially for fighter aircraft, I need to know commercial as well as for fighter. Similarly, ships. How to design a data link for these types of networks. For ships, let me just see if I can address that. For communication with ships, in fact, this is probably one of the good channels to work with. So let us say that you have the coastline, and you have the water, and if you have a tower and a ship that's in the water. Okay, so I have an antenna that I can reach to. Now notice that this will be line of sight, no obstructions. There can be a reflection of the surface of the from the water, but apart from this, there is almost no other component that will be received by this by the vessel. So in fact, over the water you can actually propagate over very substantial ranges. So communication over a ship, over water, I would say, is relatively easier to handle. Whatever you design on a terrestrial system will easily work over the water as well. And particularly for GSM, uh, initially GSM was designed as a system with a maximum range of 35 kilometers. However, for applications in maritime, they have something called an extended range GSM, where they have made some minor changes to the timing adjustments of GSM, and this can go to over 100 kilometers. It can actually communicate with the ship. Same GSM, the same receivers can now work with range. So communication over water, I would say, is something that is provided in the system. It's well understood, and therefore something that we can take advantage of. Okay. Next question. Why the downlink has higher frequency than the uplink? Okay, very, very simple reason. Base station, mobile. So let me first draw the downlink and the uplink. Green is the uplink, red is the downlink. Okay, so typically when we look at wireless systems, the losses increase as the carrier frequency increases. Okay, so this is a rule that is true in general. So as you go to higher and higher frequencies, you will find that the losses in the propagation, in losses due to absorption, several other losses actually increase. So in a nutshell, we make the assumption that this is the base station, this is the mobile station. The transmit power of the MS is substantially less than the transmit power of the base station. So we want to give that link which has got less losses to the one that has got less transmit power, because remember, both must be able to hear each other. So in general, the typical method says, okay, the mobile has got less transmit power, so let's give the channel with a lower frequency. So basically, we say that the frequency on which the mobile has to transmit, which is the uplink frequency, will always be less than the frequency on which the base station will communicate. And that is the reason why the frequency of a downlink invariably is higher than that of the downlink. So you would always find that whenever we do FDD allocation, so you will first have the uplink band. There is a gap for the duplex spacing, and then you will have the downlink band. So if I have a particular channel for the uplink, the corresponding channel will be here in the downlink, and the duplex spacing is the spacing between the transmit and receive channels. So this is the duplex spacing. We do have the separation between transmit frequencies and receive frequencies, and but even among that, which one to give to the mobile, which one to give to the base station, the assumption is that the mobile has got less transmit power, and we know that losses will increase as the carrier frequency increases. So therefore, give the mobile a lower transmit frequency. And when does the mobile transmit? Mobile transmission is during the in the uplink direction. Okay. Another question. There is a email with the output of network info 2. would like to know what the parameters are, yes, we'll take a look at the email and then describe the what the different parameters that are mentioned. We'll take a look at that mail and then be able to help you with that. Yes, that is the question number 6. Question number 6 happened to do with the network info. This is a software tool that we can download for Android phones, which you can then use to monitor the signal strength from the different base stations. I believe I have a slide on that. I'll see if I can pull up that. Maybe that will help. But if there are more questions, I'll go back and take a look at the email. Okay, so this is what is a screenshot of the system that you will see in the network. This is a software called Network Info 2, and this is what the screen will look like. It will tell you name of the operator, the country. It will give you 2 numbers. It's a combination of 5 digits. MCC stands for country code, mobile country code, and MNC stands for mobile network code. It will tell you whether it's a GSM or Edge type of network. Then gives you a number of interesting pieces of information. One is a cell ID, and the next one is a location area code, LAC. Now, location area is the identification of those cells where a particular paging message will be sent. So you can look at the expansions for each of the acronyms on the next slide. This is part of the week 1 information. We have a reading called RSSI, Received Signal Strength Indicator, and it is translated into equivalent number, which is called the arbitrary strength unit. Okay, so what we have is the conversion. If you're looking at a dBm signal, the conversion between the arbitrary strength unit and the dBm value is given here. So basically, when you look at the received signal strength, it will be some small number, minus 85 dBm, minus 100 dBm. These are all very small values. You translate it from there to a number which is in a is a positive number in a range that is between 0 to 31. So that is typically what the representation. You can look at it in RSSI, or you can also look at it in terms of the these arbitrary strength units. Okay, so this is what a screen should look like, and we'll be happy to take a look if you have attempted to see what your screen is showing, and if there are particular fields that are not you're not able to understand, I will be happy to explain those. So what you can find is there is a base station to which you are connected to. So that has got a particular location area code, and there is a signal strength that is associated with it. Now you find that there are other neighbors whose signal you're able to pick up, and they have their signal strengths as well. Now, the important thing to note is that if there is another base station which is substantially stronger than your own, then at some point the network may permit a handoff. Now, in this particular example, let's take a look. The one of the neighboring base stations is at minus 89 dBm, 4 dB lower than your own base station. The other two are also not as strong. One is minus 103 dBm, the other one is minus 99 dBm. So in this particular case, there is no compelling case for a handoff. However, if you continue to move and this minus 85 eventually becomes minus 100, then you may be looking to do a handoff with your neighboring base stations. So that is how, and it's very interesting. You can also walk from one point to another. You can also see if during that period there has been a handoff between one base station to another. That will also be an interesting experiment that you can do, which is what we had asked. We typically ask our students in the camp when we're doing this course on campus. We ask them to move around and look at the signal strength measurements and then see if there has been a handoff. And if there has been a handoff, can we explain why the handoff occurred? Did some other base station become substantially stronger, or was there an obstruction to the base station that you were currently communicating with? Either of those cases may cause maybe a reason for a handoff. We can then look at the explanations. So this is network info. If there are any questions, I'll please drop me a mail. I'll take a look at it and then respond to that. All right. Any other questions from the students who are online? Where do I? Refresh.
Yeah, that's it.
Okay. One more question. How and when to select QAM, BPSK, 16-com, 64 QAM modulation? For this also, I think we have a slide. Let me see if I can pull up that slide. Here it is. So one of the key things that that we recognize is that when we want to transmit more information to a user, the correspondingly we need to allocate more resources. Either we have to have more resources in terms of bandwidth or in terms of power. So when we have a limited amount of bandwidth and you want to increase the information that is sent to a particular user, then we have to permit an increase in power. So when does the power increase naturally happen? If you look at the base station as this building, located in this building, and the three tiers that are present because of geographical distance. There are people who are close to the base station, that's the yellow ellipse, then somebody who is in a medium distance, blue ellipse, and then finally the red ellipse. Now, because of distance, there is propagation loss. In all likelihood, the users in the yellow ellipse are seeing a higher signal strength than the users in the red ellipse. So in principle, the SNR experienced by a user in the inner ellipse will be higher than the user in the outer ellipse, and therefore we now have intrinsically a differentiation between the SNR. The base station is transmitting with the same power level, but when it's received by the receiver, the receiver who is close to the base station sees a much stronger signal. In this scenario, if you have adequate signal strength, you can change from, let us say, a modulation where you're transmitting either 1 bit or 2 bits to QAM. Assuming you have improved signal to noise ratio, you can go to a 4 bit per symbol transmission. If you still have better signal strength, you're able to achieve the necessary signal to noise ratio, you can actually go to 64 QAM. So a lot depends on the link conditions. One is with what power the base station is able to transmit. The second one is how far away from the base station are you, how much signal are you picking up, and if there is any strong interference. Anytime you have strong interference, you will find that your signal to noise, signal to impairment ratio goes down, which means that you will not be able to support these modulation schemes which require high signal to noise ratio. So you would have to then fall back to the QPSK. So let me summarize it in the following manner. I will add a slide and then explain. Base station, mobile at a distance 1, mobile at distance 2, mobile at distance 3. So this is 1, 2, 3. Okay. This is the mobile that will have the weakest signal to noise ratio. So we would measure it by this is the desired signal. This is desired signal. Any other base station whose transmission happens to reach is a interference. So what we would have to do for each of these mobiles would be to measure signal to interference plus noise ratio, SINR. So this would be signal to noise plus interference. Okay. In some cases, the interference may be higher. Some cases, the noise may be higher. Ultimately, we are looking at this ratio. So this ratio more or less determines what modulation scheme we can support. Now, notice that as you move closer to your own base station, you're moving farther away from the interfering base stations. So therefore, if I write this down as SINR1, this as SINR3, SINR3 will be greater than SINR1 on average. This will be the condition that is true, and therefore the number of bits per symbol that mobile 3 can use will be greater than the number of bits per symbol that a mobile at location 1 would be able to transmit. So again, to answer your question, we would have to actually compute or estimate what is the signal to noise SINR that is being experienced by the user, check whether the SINR is adequate. So you would have to go back and look at the BER versus SINR graph. So you may see a graph like this. If I have a target SINR at a particular location, then I go ahead and look at what is the bit error rate. Typically, we would like to design the bit error rate for a 10 power minus 3 bit error rate. You check whether the SINR is sufficient to reach a bit error rate of 10 power minus 3. If it is not sufficient, so let us say, for example, the SINR that you have is here. Okay, so this is we are looking. This is the plot for 64 QAM. Let us say 64 QAM. So what you have is only an SINR which will not give you a 10 power minus 3. In which case, then what you would have to do is go in and change the modulation scheme to something that is more robust. So maybe you want to go to QPSK so that this SINR will still give you good performance. So this is broadly what the criteria that are used for the design of a system. Understanding what the SINR is, what is the bit error rate to SINR for the different modulation schemes. So you would have a family of modulation schemes. So that would be 64 QAM, 16 QAM, QPSK. So basically we can label them as 64 QAM, 16 QAM, and 4 QAM. Okay. So notice that for a given signal to noise ratio, the best performance that you will get is for the 4 QAM, because you're using you're trying to send less information. Depending upon what SINR we get, we can make sure that the threshold of 10 power minus 3 is achieved. So if 10 power minus 3, this is the threshold at which you can transmit 4 QAM. This is the threshold at which you will be able to transmit. Any SINR better than this, you can transmit 16 QAM. And similarly, you have a threshold for 64 QAM. So you use some guidelines like this to design your cellular system, so then we can design a very robust system. Okay, let me see if there is one more question that has been posted. Let me read out the question and then try to answer it. Okay. The question is how we want to select 16 and 64 QAM. I hope the explanation here would answer that. Next question from Shinu Agarwal. In lecture 14, you said that time resolution is inversely proportional to the bandwidth. Then for large bandwidth T, time resolution will be more or less. Okay, let me see if I can explain this. The link between bandwidth and time resolution. So let me denote the bandwidth of the signal as BW and time resolution as delta tau. Time resolution as delta tau. Okay. Now, what we said was the uh, delta tau is inversely proportional to the bandwidth. So basically what it says is the larger the bandwidth or higher the bandwidth, the time resolution goes down. So what we mean by this is if I have a 1 megahertz bandwidth signal, the time resolution becomes 1 microsecond. Okay. Now, if I have a 10 megahertz signal, that means the bandwidth has become 10 times larger, then this would correspond to zero point 0.1 microsecond. So maybe it improves. The wider the bandwidth, the time resolution becomes better, 0.1 microsecond. So in other words, whenever you have a wideband signal, you are able to differentiate between two copies of a signal. So for example, if I have, if you go back to the diagram of a multipath channel, I will just draw two reflections. And here is the mobile. We get two copies of the signal. Okay. Now, if you want to visualize it, transmitted one pulse, another copy of the pulse came a little bit later. Now, what we mean by time resolution is, can I tell that these two are two pulses, or will my receiver say, well, you know what, I received something like this, something a little bit wider. I don't know how many pulses there are. So this is a case where I do not have a sufficient resolution, time resolution. This is a case where if I'm able to tell that there were two distinct pulses, so the time resolution delta tau that we're talking about is that spacing which you can differentiate when multipath components are arriving. Okay, so now this delta tau, this ability to resolve becomes better. That was, for example, 1 microsecond for a 1 megahertz signal, 0.1 microseconds for a 10 megahertz signal. So basically, you will be able to tell delays of 0.1 microsecond once you have a bandwidth of 10 megahertz. So I hope that answers the question of the relationship between bandwidth and time resolution. Wider the bandwidth, the better the time resolution. What we mean by better is you can resolve the multipath components arriving at much closer, with much closer spacing in terms of time. Okay, next question from Krishna Kant. If a user wants 10 megabits per second in CDMA, okay, very good question. Let me see if I can read the full question. Then he needs 10 megahertz bandwidth without spreading. With a spreading factor of 64, a user requires 640 megahertz. But you have mentioned in the video that a user requires 64 megahertz. Okay. We'll have to you'll have to give me if you can give me the specific link, the point at which this particular calculation were done. But let me address a broader question. So which take the question of CDMA and high data rates. Okay, very, very important question, because I can also clarify the specific numbers, but let me give you the broad framework. Supposing I have a ability to transmit, let us say 64 kilobits per second. 64 kilobits per second, and I use a spreading factor of 32. Spreading factor of 32. Okay. Now, of course, we'd have to worry about what is the bandwidth required. It will be proportional to the bit rate and the spreading factor that we are using. The second element, supposing I want to increase this to 128 kilobits per second. We can do it in two ways. You can retain the spreading factor of 32. And in whatever was the bandwidth, let us say the bandwidth required was B here. now you will require a bandwidth of 2B, which is exactly what you have pointed out. You've increased the data rate by a factor of 10, and therefore you have multiplied it by the. Now, it doesn't necessarily have to be in this particular case. You can also do, you can reduce the spreading factor. You can double the data rate, but reduce the spreading factor by a half. So in this case, the bandwidth will still be equal to B. Okay. You can do yet another thing. You can actually allocate multiple spreading codes can be allocated to this user. So 2 codes with spreading factor equal to 32, which means that the bandwidth is still equal to B. So higher data rates in a CDMA system are achieved by 2 mechanisms. One is reduction of spreading factor, and the other one is using multiple codes. We can use both of these techniques using multiple codes. Now, with respect to the question that you have mentioned, I would have to take a look at the specific numbers, but by and large, it should fall into this category. Using multiple codes, you can achieve high data rates, you can reduce the spreading factor and achieve data rates. If you do not do that, then the bandwidth expansion will occur. Okay, so that is a quick summary of the points mentioned. Now, let me see if that address the questions. If a user wants 10 megabits per second in CDMA, then he needs 10 megahertz bandwidth without spreading, again, assuming that you're using a binary modulation. So binary modulation, 10 megabits per second will require a bandwidth of 10 megahertz. That is correct. Now, if you want to introduce spreading factor, then it depends on what modulation method what modulation we are using. But anytime you want to increase the data rate, you would encounter these types of the 2 options. You can either keep the same spreading factor, you would have to increase the bandwidth, or you can do reduction of spreading factor and increase by multiple codes. Reduction of the spreading factor. Okay, those are 2 methods. Let us see what is the next question. What is the future of WiMAX? Why is it okay? As we speak, the WiMAX as a potential candidate for 4G and beyond is not something that is part of the cellular roadmap. Pretty much there are users and applications of WiMAX, but no major evolution path for WiMAX. So I would say that there are current usages, but in terms of the major evolution that is happening, most of it is happening in the context of LTE and not in the context of WiMAX. Okay. What is the future of WiMAX? We have made a brief comment about it. Maybe if there are more questions, you can raise that. Krishnakant has posted another question. In the overview of cellular systems, part 2, lecture 2, at 42nd minute. I don't know what is your question. But okay. So what we will do is the TS and I will take a look at what you have, the point at which this particular calculation is done, and then maybe post it on the discussion forum, or in the next week's online discussion, we will handle that. Okay, question from Shinu Agarwal. What is the difference between bandwidth and... Oh, very good question. Very good question. Okay, they are completely different concepts. The first one is bandwidth is how much frequency resources the signal occupies. Okay, so minus W by 2 to W by 2, complex baseband signal, two-sided bandwidth equal to W. So this is if you write down a complex baseband signal, and it has a two-sided bandwidth of W. When you modulate it, in the process of converting from baseband to RF, the spectrum will now become, the spectrum of the signal will no longer be at, it will get shifted to a carrier frequency FC, and you'll have a mirror image at minus FC. Okay, basically the mirror image of that, and this is what a band pass signal, or the modulated signal representation will look like. What is the bandwidth of the modulated signal? We usually talk about a one-sided bandwidth for a modulated signal, therefore it is W. Okay, W is the bandwidth. It's two-sided bandwidth if you're talking about a complex baseband signal. It's a one-sided bandwidth when you talk about a modulated signal. Now, this is bandwidth. Now, what is coherence bandwidth? Coherence bandwidth, the best way to understand coherence bandwidth is that when you look at a transmission of a signal, I can transmit at a frequency F1, I can transmit at a frequency F2, which is close by, or I can transmit at a frequency F3. Okay. Now, let us assume that I am transmitting a narrowband signal. So, which means that I have a signal which occupies bandwidth which is centered around F1. The channel will introduce a certain gain. So, let us call that as G1. Now, if I shift by only a small, if the carrier frequency shifts by only a small amount, then this will be G2, and in all likelihood, G2 is very, very similar to G1. This is because there is a correlation in the behavior of the channel, and therefore, when you look at closely spaced center frequencies, they will likely to have channel gains which are very similar. On the other hand, if I shift over to F3, I may have a much larger gain. Okay, so this could be G3. This is a gain that is completely uncorrelated with the gains that I saw at F1 and F2. Now, the coherence bandwidth is a measure of what is the distance in center frequency when we move by that bandwidth, I will see a completely uncorrelated channel. Okay, so this is the delta F. What is the spacing in the center frequencies such that the channel gains are uncorrelated. Channel gains are uncorrelated. Okay. Now, when would we want to do this? This is for the process of frequency hopping. The reason we do frequency, one of the reasons we do frequency hopping is that your current signal or the current center frequency may be experiencing a gain which is not very good. So therefore, the user may hop in frequency. So G1 to G2, F1 to F2 to F3, back to F4. Maybe there is an F4 which is situated here, also experiencing good channel conditions. Okay, so this could be F4. So frequency hopping is a technique that is used to keep changing the center frequency of the channel so that you get to experience both good channels and occasionally a bad channel. But the advantage of the good channels is what you want to leverage. Now, by how much should you change the center frequency? So the when you do frequency hopping, you get the maximum benefit if the change in the center frequency, maximum benefit if the change in center frequency is greater than the coherence bandwidth, So notice that for narrowband signals, the notion of coherence bandwidth tells you when you can get frequency diversity. By what center frequency should I change in order to get the advantage? Now come look at what is the effect of coherence bandwidth. coherence bandwidth for wideband signals. Wideband signals. Okay, so here is the, let us say, is the representation of channel gain versus the frequency, carrier frequency or center frequency. Let us sketch some arbitrary waveform. Some gain term, gain has been present. So for a narrowband system means that I transmit like this. I change by coherence bandwidth, then I have another frequency narrowband and another one. So basically, each of these have been separated by some larger than coherence bandwidth. Notice that the channel has gone from good to bad to good once again, and that's because you have separated your center frequencies by more than coherence bandwidth. Now, on the other hand, if I had a wideband signal, a wideband signal is, this is a wideband signal. Wideband signal by definition has a bandwidth which is larger than coherence bandwidth. So which means that within the frequency content of a wideband signal, the channel gains will be different. Therefore, the frequency response of the channel will distort your signal. Okay, so for example, if I transmitted a spectrum that looked like this through through a system where it was the channel gain was a flat response, then what will happen is when it passes through, it remains in the same level. Only the gain, it may increase in amplitude, increase in gain or reduce in gain. So this is what happens to a narrowband signal. The narrowband signal sees a flat channel response, right? It either is good or bad. But on the other hand, a wideband signal does not see that. Wideband signal, to begin with, much wider bandwidth. When it comes to the other side, it sees some spectral distortion. So this means that we must compensate for the distortion introduced by the. So wideband signals are by definition have a bandwidth which is greater than coherence bandwidth. So the channel will change, and when the channel changes, it distorts the signal. So you must compensate for this distortion. Now, typically, this distortion manifests itself as intersymbol interference. And we know that whenever you have intersymbol interference, you must have some form of equalization. So wideband signals with bandwidth larger than coherence bandwidth absolutely must have an equalizer. Without that, you cannot receive the signal because the signal gets distorted. On the other hand, narrowband signals, you may or may not need a equalizer, depends on the channel. But by and large, when you have a narrowband channel, all of your frequencies are seeing the same gain. So therefore, there is no channel-induced distortion in the spectrum. So that is, I hope that clarifies the difference between the coherence bandwidth and what is the importance of coherence bandwidth for narrowband signals and what is it for wideband signals. Okay, let's see if we can pick up what was the next question. Why is CDMA more used in US and GSM in Europe? Okay, very interesting question. So you have US, you have Europe. There is CDMA very widely used. That is correct. This is GSM. But as we look at the evolution of these systems, we saw in the US, this went to a technology called CDMA 2000. This went to a technology called wideband CDMA. And interestingly, this went to a technology called LTE. This also went to a technology called LTE. Okay. Now, historically, why were in the earlier days? Why was there difference between the two schemes? Um, uh, Again, the technologies evolved from the GSM actually originated in Europe. It was a standard. It's a pan-European standard. At that time, so this was a pan-European TDMA standard. Pan-European. Now, if you go back and look what happened before this, there was a technology called US Digital Cellular. Now, that was a Pan-American TDMA standard. Pan-American TDMA standard. Okay, if you already have a TDMA standard, your market may not be necessarily ready to adopt another TDMA standard. So when GSM was introduced, by that time the US Digital Cellular was also being developed. So basically both those things were introduced into the market. There was a Pan-American standard, there was a Pan-European standard. Now, as the technologies were evolving, the CDMA technology was developed with a significant amount. I wouldn't say completely, but a significant amount of technology development from the company Qualcomm. And from them came a lot of the basic concepts that would be used, concepts such as soft handoff, which were essential for the building of a cellular system, came from Qualcomm. That was developed and was first introduced into the US market. By that time, GSM had already been completely deployed all across Europe. So therefore, it was a well-established standard. Therefore, they did not want to change over to a new standard. But when the time came for the evolution to occur, the advantages of CDMA were recognized. And therefore, they came up with a version of wideband CDMA which had similar features, but there were some incompatibilities. So therefore, this technology in the US side evolved to a technology called CDMA 2000, had similar features, spreading factors, multiple codes, power control, soft handoff, all of those things, similar things. These two were similar in terms of their features, but there were some essential differences as well. But moving forward in the 4G time frame, both are OFDM based, and therefore they are both using the same technology. So it goes back to a little bit of history, who developed which technology, which one was deployed earlier in that region, which one the operators chose. So of course there'll always be debates as to which is better. But at the end of the day, there are more factors than just the technical comparison. There's also what type of investments have been made, whether the return on investments have been fully realized, and if there is still a market for for a particular technology. So that, I hope, will give you a little bit of what the history behind CDMA and GSM are. Okay. Krishnakant, lecture 46 on gold codes and Kasami codes is missing. Okay, we'll make a note of that. There's a lecture 46 is missing. We'll take a look at that. Huh? Okay, maybe the link, we'll send you another link where the lecture 46 is available. Okay. Okay. So if you would just send us a mail, we'll send you a link to where you can locate lecture 46. Okay. Shinu Agarwal, do same discussion follows for coherence time. Okay. Coherence time, let me address it in this fashion. If you remember, we drew the time varying channel using a three-dimensional representation. Okay, so if I look across time, so this is, if I think of this as amplitude, this is the time axis, this is the delay axis. Okay, now looking across time, so looking across the different time indices, I look for a particular channel's behavior. Strong, continues to remain strong, starts to decrease, starts to decrease, eventually becomes very small, and then again starts to increase. You can see how the time variation of this particular, there's only a one tap channel. Now, just like we talked about the correlation between the channel gains across frequency, we will now talk about correlation in channel gain across time. Okay, channel gain. So single tap H of t. Okay. Now, basically, we are looking at the correlation between H of t and H of t plus delta t. By what value should delta t be changed such that the channel looks substantially different? So yes, the notion of how much correlation is present, how different is the channel for the different time instances is what we are trying to measure. So in that sense, you are correct. There is an analog. It is analogous to what you would call as the coherence bandwidth. So coherence time is the time for which I can assume that the channel is reasonably correlated. Once I exceed coherence time, so for example, if I were to observe the channel at this point in time and at this point in time, I would come up with a completely different channel gain terms, and they would be uncorrelated. So this is saying that this separation, which corresponds to, let us say, this is T1, this corresponds to T2. So this separation, T2 minus T1, is much larger than coherence time. That is what would be our conclusion. So on the other hand, if I looked at another observation, let us say this is T3. T3 minus T1 is less than coherence time because they are highly correlated in terms of their channel gains. So that is how I would interpret channel gain. If there are any specific questions, I'll be happy to answer them as well. Okay. Now, Krishnakant, lecture on OFDM in week 12 is also missing. Okay, you are going a little bit ahead. Yes, the videos for in the NPTEL course, there may not be, because we were limited to contents for 12 weeks, but there are videos for the OFDM content, which will give you the link. So if you don't mind, just give us a mail. Currently, the plan for the 12 weeks you can see on the course webpage. But though there is a brief reference to OFDM, but a detailed lecture on OFDM, we can give you a link for that. Please send us a mail on that. Okay, a question from Analog Techie. GSM, is it a wideband or a narrowband signal for voice calls? Okay, so here is how we would define it. Is GSM bandwidth 200 kilohertz? Okay, most of the channel conditions under which where we operate, the coherence bandwidth is typically greater than 1 megahertz. Okay, so in many environments or observations, you can treat GSM can be treated as a narrowband signal. Having said that, GSM does suffer from GSM signals are affected by ISI. Where did the ISI come from? If it was a narrowband signal and the channel was flat, that means there is no channel introduced ISI. This ISI partly comes from the modulation. Okay, GSM uses a modulation method which falls into the category of what we call as partial response signaling. partial response pulse shaping. Okay, we call it partial response. Partial response pulse shaping. This definition is that the pulse shape that we use has a duration greater than t. Duration greater than t. That means more than one symbol duration. Okay, your pulse. So if this is one symbol period, a full response signaling would mean that you have a pulse shape that looks like this. GSM, on the other hand, uses a pulse shape that has a wider. Okay, so even though the channel does not introduce ISI, there is ISI present because of the way you have generated the signal at your transmitter. So GSM is affected by ISI, but the channel in many cases will not affect us much. There are some highly dispersive channels. So, for example, if you are in a very densely, a lot of buildings in a urban area, which you call as a typical urban or a bad urban area, then which means that there is a lot of multipath. Then what you would find is that in those channels, the coherence bandwidth would be less than 1 megahertz. So therefore, GSM also starts to behave like a wideband signal. But by and large, GSM can be treated as a narrowband signal. It is affected by ISI partly because of the modulation. So that is the. So if to answer your question, is GSM wideband or narrowband? I would say predominantly you would classify GSM as a narrowband signal. Okay, next question from Krishnakant. Factors affecting hop rate in frequency hopping spread spectrum. Okay, so the elements that we are trying to achieve in a frequency hopped spread spectrum. There are two elements to this. The first one is what we call as the interference mitigation. Interference mitigation. How fast should you hop so that you are not affected by a strong interference? Supposing that you're on a frequency F1 and there is a strong interference that is coming in. Interference. Okay, now then what you do is you change from frequency F1 to F2 to F3 and so on. This is frequency hopping. Now F2 does not have much interference, but F3 has got a little bit of interference. Okay, and then so on, F4. So what are we doing by changing the frequency? By doing frequency hopping, we are mitigating interference. You're not getting stuck on a center frequency where there is a lot of interference. So you're basically doing what is called interference averaging. Interference averaging. Now, how frequently you have to hop to avoid to get the benefits of interference averaging? A lot depends on the type of interference environment that you are in. Supposing you are like Bluetooth, you are operating in an environment where there's a lot of interference, then you would actually do very frequent hops. In the case of GSM, you're doing interference averaging. Most of your interference is coming from other GSM users who are also part of your own system. So therefore, it's not an uncontrolled interference environment. So in that case, the frequency hopping is done at a slower rate. So again, it is to a large extent, it depends on the interference environment in which you find yourself. Okay, next question. Please keep the link of lecture on course portal so the participants can read it. Okay, the thing is, the videos for the course are actually all available in the NPTEL course. But some of the things that I'm referring to are to lectures not given as part of the NPTEL course, but as part of other courses at IIT Madras. So that's the reason why it's not on the course portal. The course portal has got all the course-related lectures. What I'm referring to are additional lectures. Again, if we try to post it on the course website, it will create confusion because the lecture numbers and the course name, everything will be different. But if you say, I would like to watch a lecture on OFDM, we can point you to a lecture which addresses those topics. not as part of this course, but has got the content that is of interest. So that's why it's some of the things that I'm referring to, okay, on OFDM or on some other topics are not, you may not find it on the website. Okay, good. If there are any other questions, we'll address them. If not, oh, there are one or two more questions. Let me quickly see if we can take it up. If frequency hopping rate is too high, is there any problem between the sender and receiver? Will data loss be there? So yes, there is a class of receivers which are called fast frequency hopping. Fast frequency hopping. Okay, so this is a case at which in which we call a hopping rate. Hopping rate. That is the rate at which you do your frequency hopping is greater than your symbol rate. Okay, so which means that if I were to look at a symbol, okay, one symbol, part of it may be on F1, another part on F2, and the last part happens to be transmitted on FM. Okay, so basically there are multiple frequencies on which you are transmitting. So these are what we would call as fast frequency hopping. These are not used in civilian systems, used primarily in the military, and they are used so that there is to make the signal transmission very robust. But to build receivers for fast frequency hopping requires very special electronics. So therefore, this is not something that we would do. This is, in fact, our transmission schemes are that where in commercial, hopping rate is much less than symbol rate. In fact, many symbols, hundreds of symbols will be transmitted on one particular frequency. This thing. So, when we say frequency hopping for commercial systems, the hopping rate is much less than symbol rate. It is nowhere near fast frequency hopping. Fast frequency hopping is something that the is used by the military. Okay, yes. So if you are doing very fast frequency hopping, there are some challenges in terms of you must be very well synchronized between the transmitter and receiver. Otherwise, you will lose the link and therefore not be able to communicate. That is correct. So next question from Shinu Agarwal. To transmit 800 megabits per second data in 16 megahertz, what modulation technique should be used? So we can take a quick look at that. So you want to transmit 800 megabits per second. You want to use a 16 megahertz bandwidth. Usually the bandwidth that you are using approximately translates to the baud rate. So the baud rate that you are using is 16 megabaud. The same, this means that you are transmitting 16 mega symbols per second. So if I want to transmit 800 megabits per second, and I can transmit 16 mega symbols per second, this means I would have to, well, this doesn't sound right. I would have to transmit 50 bits per symbol. No, something looks wrong in this. Let me change the problem. Let me change it to 80 megabits per second. Okay, you can then see what the links are. So if I want to do 80 megabits per second, I would have to do 5 bits per symbol. This would be typically a 32 QAM, 5 bits per symbol. But what you may want to do is take 64 QAM and apply rate 1/2 coding. Okay, so 64 QAM at 16 megabits, 16 mega symbols per second, into 64 will carry 66 bits per symbol, right? And this will this will carry you to 96. 16 6s are 96 megabits per second. Okay, so well, I can't do rate 1/2. I would have to do a rate 5/6 code. Is that correct? 16/6. Yeah. So if I introduce some channel coding, then with channel coding, the information rate will drop from 96 megabits per second to 80 megabits per second. Okay, so of course, you can do exactly 32 QM, in which case you will get 80 megabits per second. You could also do 64 QM and give yourself some room for channel coding. Okay, we have exceeded the time. Let me just see if we can quickly answer any more questions. Otherwise, we would introduce it, take it up in the next class. Where are memoryless nonlinear digital modulation FSK used? GSM is a modulation with memory, and it is nonlinear. So yes, FSK is the broad family. What GSM uses is Gaussian minimum shift keying, which is a special case of the FSK family. Okay. Up to what traveling speed our cellular communication can happen? Good question. GSM is designed for 350 kilometers per hour, up to 350 kilometers per hour. That's GSM's. But today they are saying that even if you are traveling at higher than 350 kilometers per hour, it is not a problem. We will be able to communicate. This goes back to a question I think you had raised. What can you do when you have very high speed motion? What do we do for aircraft? Sometimes we carry the base station on the aircraft, okay, which means that the base station is also traveling with you, and then you connect the base station to other devices via geostationary satellite. So the effect of Doppler is actually removed from the scenario. So on a high-speed train, you could carry the base station on the train, and then take the communication back to the rest of the network through some other means, so that the effect of Doppler is minimized. So yeah, there are several solutions for doing communications on high-speed vehicles. Definitely something that will be addressed in the has been already been addressed in the cellular environment. Okay, I think that brings us to the end of the discussion session today. Thank you to all the students who joined us. There were a few action items. I think we will respond to that. And if there are any points that you would like to highlight or some feedback that you'd like to give, please send an email. Let me just write down my email ID: davidk@iitm.ac.in. That's the best way to reach. Please do mention that you are an NPTEL course student, so therefore I'll know the context in which the question is being raised. Okay, thank you very much. We'll connect with you next week. Thank you.